Hello, I'm Nikhil Kolachalma.
I'm Sheikh Mahmood.
I'm Roshindana Shaker.
I'm Elizabeth Mishkovich.
And I'm Ava Tan, and our project is the optimization of four-way controlled intersections with autonomous and human-driven vehicles.
I'm sure as drivers you have all experienced some sort of confusion at these types of intersections. Now, this type of confusion actually accounts for over 40% of fatal car accidents at these intersections to occur.
So in order to tackle this solution, or this problem, we're aiming to make a software-based solution for these types of intersections to reduce the number of accidents.
For this presentation, we'll begin by giving background information and explaining the components and concepts we used. Then we'll move on to the development of the smart car, the environment, and the training data set, along with the implementation of the computer vision algorithms. Then we'll move on to the results, where we'll discuss the object detection and position detection data. And finally, we'll conclude with our findings, future goals, and acknowledgements.
So moving on to the background, these are some of the main parts that we use to construct our autonomous vehicle. The first part is the Arduino Uno itself, which is a microcontroller that is compatible with various motors and can interact with many accessories such as LEDs and cameras, and this is through input and output pins. The other major component is the Microsoft LEDCam 3000, which is just a camera that is placed above our environment so it can have a top-down view of our intersection. And this way, the camera is able to detect where the self-driving cars and the human-driven car are so we can prevent accidents. And these are some of the sensors that we use. The first one is the ultrasonic sensor, which detects how far away an object is from the car's location, and this can be used for obstacle avoidance. And the other sensor is the light sensor or the tracking sensor, and this can be used so that the car can follow a line. And on a real-time situation, it would be used so that the car can stay within its lane.
Okay, so to basically explain the scope of our project, we're working under a computer science-based project, of which two umbrellas we're working under. So that's computer vision and machine learning. So these two things aren't mutually exclusive of one another. So the algorithms that you use with computer vision are also used with machine learning, and they intersect with one another. And a special type of algorithm known as deep learning is also used. And computer vision, machine learning, and deep learning also intersect with one another as such, so that you can use convolutional neural networks with computer vision.
Computer vision aims to give computers a visual understanding of the world and simulate human vision. This process is carried out in three main steps: image acquisition, which involves taking photos using a traditional camera and transferring these images into binary data; then image processing, which utilizes various algorithms to analyze the low-level information of images, such as the basic structures and the lines of the images; and then finally, image analysis and understanding, which utilizes higher-level algorithms to incorporate the information that was obtained in the previous steps and actually recognize objects within the images.
Supervised machine learning was used to train our neural network. It is named so because the data scientist acts as a guide to teach the algorithm what conclusions it should come up with. The first step of supervised machine learning is to compile the data set. For our sake, this involved taking over 2,000 photographs of the intersection with the cars in various configurations. The next step is to annotate these images. Annotation included putting bounding boxes around each car in the intersection and classifying it as either an RC car or a smart car. And lastly, we use these images to train our neural network.
Another component is deep learning, and deep learning is a subset of algorithms underneath machine learning. And the primary algorithm that deep learning uses is neural networks, which functions in a similar manner to the brain. So think of each of these components as a neuron. Some of these act as a trigger and send a signal, like an input, while the others would receive that signal and do a corresponding action, like an output. The connection made between the input and output is known as the hidden layers. And this connection is determined based off of the weights of those connections between each of the neurons. So for example, one of the connections between the neurons could be weighted 0.9, while another could be weighted 0.1. So the most probable path that the neurons would take would be the one weighted 0.9. And using these connections, we can make paths between the input and output layers. And over time, as the brain increases its power to recognize images, the neural networks would be able to better predict the locations of the objects, or in this case, the cars.
Under deep learning is an algorithm called convolutional neural networks, which is also a subset of computer vision. Convolutional neural networks use images as inputs as they analyze each section or a small section or feature of an image rather than the entire image as a whole. So the first step is convolution, a mathematical operation that compares a feature with every part of an image. The next step is pooling, which is a method that shrinks down a large image while still maintaining the most important information within it. Another important facet of convolutional neural networks is a rectified linear unit, which changes any negative numbers from the convolution to 0. In the deep learning process, a smaller set of filtered images is created from raw images that are rectified, filtered, and pooled. This process can be repeated multiple times, so you can have layers that include both the simple details of an image to the most complex details. So the next step in our procedure was building the actual autonomous car. So in order to build the base model, we used a robot car kit. The main structure of the car consists of 2 chassis, an upper and a lower. So the lower chassis contains our 4 motors, a motor driving module, our 4 wheels, as well as our 5 tracking sensors. On the top chassis is our Arduino Uno, our ultrasonic sensor, as well as the 2 3.7 lithium-ion batteries that power the car.
Moving on to the software part of our car, the first part that we programmed is the line following. And how we did this is first to set the center position of the car at case 2, where the light sensor is halfway between the black line and the white line. So this allows the car to move in a straight path. And if there is any curvature in the line, the car would run into cases such as case 1 and case 3, where there's either too much white or too much black. So if the car runs into a situation where there's too much white, it would turn to the left and orient itself back to its ideal center position. And in the other hand, if there was too much black, it would turn to the right. And the other program that we wrote is obstacle avoidance. And basically what this does is if there's an obstacle a specific distance away from the car, then the car would stop and wait for that obstacle to move before proceeding forward. And if there was no obstacle to begin with, then the car would just continue moving forward until it reaches an obstacle.
This figure is a diagram of the environment that we constructed. As you can see, it is shaped in a figure 8, so the smart car can drive around continuously in a closed loop. The roads have 2 lanes heading in opposite direction, and in the middle of each lane, we put black electrical tape for the smart car to track using its sensors. The red dashes represent the stop sign, and all these components of the environment were made out of poster paper. In order to construct the camera apparatus, we used 2 metal tripods and a metal beam, and we suspended the camera over the center using a zip tie, and we angled it down to make sure that it had an aerial view of the environment. And in order to simulate an integrated environment of human-driven and autonomous vehicles, we drove around 2 RC cars, and they represented the human-driven cars. This environment ensured that there was no confusion among drivers, as the system clearly indicated which vehicle had the right-of-way. And in addition, it also increased the efficiency of the intersection because there was no more extra time elapsed among drivers as they tried to figure out what subtle signals meant. And here is a picture. This is a picture of our actual environment that we constructed back in our hall.
So as the RC cars and the smart car drive along the 4-way intersection, the camera takes images. And this camera is connected directly to the computer, which is running computer vision algorithms to detect the arrival of the cars.
So moving on to the machine learning aspect of the procedure, the first step was to assemble the training data set. In order to do that, we used a program called LabelImage that allowed us to use our training data set that we compiled from a video and parse using a Python program to draw bounding boxes around the objects that we want to detect. In our case, that would be the RC cars, which represent the human-driven vehicles, and the smart car kit, which represents the self-driving vehicle. So here's a diagram. The next step is actually executing the training job. So in order to do that, We use Google Cloud since their GPUs are fairly powerful, much more powerful than Macs. And we executed a command using Google's TensorFlow library, which is essentially their machine learning, their open source machine learning library. And the training process itself took about 10 hours to complete, and in the end, we had a set of files that we could use with object detection program. And then the next step was actually coding the traffic rule logic. So in order to do that, we used TensorFlow's default object detection program, and we created our own indexer algorithm for tracking the positions of the cars in the intersection.
So moving on to the results section, over here on the left you can see an image of our fully constructed autonomous vehicle, and on the right is an image of our vehicle running the line tracking program. And on the next slide, we have a short video of our robot running the obstacle avoidance program.
So this figure shows the output of the neural network detection software, detecting both the RC cars and the smart car. And as you can see, it is excellent at detecting both of these types of cars and can even recognize both of the RC cars at the same time. However, unfortunately, the detection program can run only at half a frame per second due to the limited processing power of our computer.
In order to determine the location of the cars, we put a bounding box in the center of the intersection. This bounding box served as an origin point, and we determined the locations of the vehicles relative to the bounding box. So the cars were either to the top, bottom, left, or right of the car. We then developed an indexer algorithm to assign specific numbers to each car in the intersection.
So for our goals and findings, the original goal of our project was to create a software-based monitoring solution to reduce accidents at four-way stop sign intersections. To do this, we mounted an aerial camera and had a convolutional neural network in order to detect both self-driving and human-driven cars. Thus far, we have successfully programmed and constructed an autonomous car, built a testing environment, as well as trained a neural network to both detect the positions of the autonomous and human-driven cars and label what number they are.
Given our time constraints and our limited resources, this research could only be carried out so far. Some aspirations we have for this study is to actually finish the traffic rule code, because we did begin it, but we ran out of time, unfortunately. Another upgrade we would like to do is to use a NVIDIA Jetson instead of our current MacBook, which is only running at 0.5 frames per second. A NVIDIA Jetson is a processor which is much better suited for machine learning than our MacBook. In addition, we would also like to add a dashboard, and onto that dashboard add a video upload option. As of right now, the camera is streaming live footage to the computer, and therefore the computer has to do its analysis live. But since it's so slow, this isn't a really good thing. If we added a video upload option, we would have less time wasted testing these dashboard features. A change we could also do to make our system more compatible with the real world is to add motion inference detection of the smart cars. What this means is that the camera would be able to distinguish among the smart car and the RC car based on their motions, because the smart car drives in a much smoother manner than its counterpart, which tends to move around in a jerky way, and it's jagged because people aren't perfect drivers. And right now we have our system determining the differences between the two cars because of their physical distinguishes, but in the real world you can't really look at a car and tell it apart that well. So we hope that by implementing that, it would make this more compatible and scalable to the real world. Lastly, if this intersection is successful with all these changes that we would like to do, we would like to test it out in a suburb and analyze its impacts.
So we'd like to thank our project mentor, Michael DeBuono, for organizing this project, along with the other Lockheed Martin mentors, Brian Kelly, Allison Boyd, Amrita Misapatia, and Chris Carpani. We'd also like to give special thanks to our mentor, Andrew Page, who is able to set us up with the Google GPUs, and we'd also like to thank Google for allowing us and providing us with those. And we'd also like to give special thanks to fellow GSET scholar Michael Ryan, who provided his amazing insight and knowledge on machine learning. And we'd also like to thank our RTA liaison, Apurva Agarwal, and research coordinator Brian Lai, and head counselor Nicholas Ferrero, who were able to organize this program and provide their support. We'd also like to thank the program directors Dean Rosen and Dean Antoine, who were able to give us this opportunity to conduct such research. We'd also like to thank Rutgers University, Rutgers School of Engineering, the state of New Jersey, Lockheed Martin, Silverline, Rubix, and other corporate sponsors for providing the funding necessary. And we'd also like to thank GSET alumni for their continued participation and support. Thank you so much for your time, and we're glad to answer your questions.
I say that even with the limited resources I have basically two questions, both somewhat hypothetical. In the real world, I know you mentioned the distinction between a human-driven car and an autonomous car, which currently coexist. What do you see as a possible solution to that? Not with the limited resources here in the experimental scenario, but in the real world.
Well, there's two ways. Oh, sorry. Well, there's two ways we could distinguish it. One is through distinguishing how they move, so their acceleration and their jerk. Or we could try to detect LiDAR signals coming from the self-driving cars. So a more feasible solution when we're implementing this in the actual world would be LiDAR. But for our own models, motion inference detection would be more feasible.
Secondly, in the future scenario, when we transition from this mix of autonomous and human drivers, which is the current period, to the future when human drivers hopefully will be outlawed and it will be just autonomous cars, what will be the effect on their ability to navigate at traffic intersections and all? What do you foresee in research?
Well, naturally, autonomous vehicles would be moving more rapidly than human-driven vehicles because they can afford to do that. So in that case, while moving through intersections, it will be much more plausible for the intersection system itself to communicate with the self-driving cars going through the intersection. And we can use a combination of LiDAR and motion inference detection to really keep a lock on these cars.
And I'd also like to add that one of the main reasons why we thought to focus on developing a software monitoring system is because of, in the near future, where there will be both human-driven and self-driving cars, there's some communication gaps and issues, especially at a four-way stop sign intersection, where humans typically, we'd give hand signals to signal who to go first, but a smart car won't be able to detect these signals, so that's why we wanted to instead use an outside system, such as the software monitoring system.
Any other questions?